I have my screen here and I haven't turned on the projector yet. All right, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. We've made it to the final week. We have one more week of classes, and then finals week, and then Christmas, which is always an exciting time. So, how's everyone doing today? Good, good. All right, so the plan for this week is to cover all these I call them kind of miscellaneous kind of niche topics in Ansys that didn't fit too well with the rest of the class, but I think they're still important to cover anyway. So just like I promised last week, the first thing we're going to do today is do harmonic response analysis in Ansys. And so we're going to go through a simple example for that. And so for those of you who are interested in using this for the final project, this would be a great workshop for you. Okay. You're not turning anything in with this, and so this is just for your own information. And so I do have a way for you to follow along if you would like. But if you just want to sit and watch, then that's fine too. Okay. And based on the poll, and actually I can show the poll right now. Okay. All right, and so this is the poll that I put out last week based on to let you guys vote on what you want to see. And so the three winners of the poll are number one is thermal simulations, and so that's what we're going to start today. Number two is fluid simulations, and so we'll probably start that. We'll probably start doing that on Wednesday. And then the last one is fatigue life. And so if we do have enough time on Wednesday after fluids, thermal and fluids are kind of the two more time-consuming ones because there is a bit of theory that we have to go over kind of beforehand. But on the off chance that we do have some free time on Wednesday, then I'll cover fatigue life analysis. Okay. But for sure, what we're going to do this week is we're going to do harmonic system response. We're going to do thermal simulations and then fluid simulations. Okay. All right, and remember the final projects are due Monday, December 20th, and so that's 2 weeks from today. Okay. All right. One more announcement that I do want to make, before we get started today is that it's the end of the semester, and so it's time for SOQs. And so if this is your first time hearing that term, SOQs stands for Student Opinion Questionnaire. Okay. And so it's your guys' chance to basically give me a Yelp review for the class, okay? And those are really important. And so, I don't want to take any class time because I know that, I do want to cover fluids and thermal simulations, but please do go and fill out the SOQs, okay? So I was just telling my last class that, I've spent basically the last 15 weeks, giving you guys feedback on your assignments to help you learn how to apply finite element analysis in Ansys. And so the SOQs are your guys' chance to give me feedback on how I'm doing as an instructor. Okay. And so it's really kind of a really cool give and take kind of relationship because the only way that I get better at this job and the only way that I get better at teaching is by reading feedback from you guys and incorporating that into my teaching. Okay. So finite elements in particular is a class that I've really tinkered with in this at this school a lot, and you guys are kind of seeing probably the fifth iteration of finite elements that I've taught in this school because I'm always really constantly tinkering with it. And this class in particular, this is the first time I've taught this class, and I took a very different approach in this class to really teach it from a perspective of, let's focus mostly on the software skills and let's learn that. Okay. So it was something really new for me. And so I would really appreciate you guys' honest feedback on how it went. Tell me what works, tell me what didn't work. Because I read every single comment that you guys give me and I really take it seriously. Okay. So please do tell me because, this is a class that I hope to teach a lot in the future and I want to teach it well. And the only way I can really teach it well is to get your guys' feedback. Okay? And please don't be afraid of being honest. So I grew up in internet culture, and so I've had people call me all sorts of terrible things online, and even in past semesters too. I've had students curse me out on the evaluations, and so feel free to use whatever colorful language that you want. It's all anonymous, and so I won't know who you are. And in fact, the ones that really the ones that cursed me. So there's only been two. And so the two students that have cursed me out in the past, I think those are probably the most useful pieces of feedback that I've gotten, because they really passionately told me how they felt about the class, and I've made changes to my classes based on what they said. Okay? Of course, be constructive. Don't just say "F you, motherfucker." That's not that's not helpful. But if you spread the cursing along with constructive things that you think can make the class better, things that I can do better, then that's the best way to use it. Okay. Okay. And so I think the SOQs are due this Friday, and so I'll send an email out in the middle of this week just to remind you. But please do go fill out the SOQs. They are. I mean, of course, they're important to the school, but they're really important to me as an instructor. Okay. Okay. So any questions I can answer before we get started today? Okay. All right, and so let's go ahead and get into it. Okay, and so the first topic that we're going to cover this week is harmonic system response in Ansys. Okay, and so this is kind of like a follow-up of Ansys Activity 7. And so if you remember what Ansys Activity 7 was about, that was when we did modal analysis, right? And so remember, the whole idea with modal analysis was to perform basically some kind of vibration analysis. And so, we basically talked about how every structure has, a series of natural frequencies. Okay. And these natural frequencies are kind of the natural frequencies at which these objects vibrate with. And so, if you do end up forcing your structure with at the frequency that matches their natural one, then you are going to get resonance, which results in very high amplitude oscillations. Okay. And so activity 7, in a way, I feel like was a little bit not satisfying because we never really took it all the way to see what resonance actually looks like. And so that's what we're going to do today. So we're going to see what happens when you actually force a system at its resonant frequency. Okay. And for the sake of simplicity, and just because I already had the CAD model uploaded onto Canvas, we're going to work with an old friend. And so if you remember from Ansys Activity 2, we ran an analysis on this bike crank, right? And so I think this kind of serves as a perfect example of how to do harmonic system analysis, and and the results for this are actually really clean as well. Okay, and so to start out with, let's go ahead and launch Ansys Workbench. And again, this is just a walkthrough, and so you're not turning anything in. And so if you want to follow along, that's great. But if you are interested in just watching, then that's fine as well. Okay. All right. So what I'm going to do is I'm going to take modal here. Okay. So we're going to start with a modal analysis. I'm going to click and drag that into the workspace, and then I'm going to import my bike crank. Okay. Brake assembly. All right, and then I'm going to go ahead and launch mechanical. All right. All right. So the first thing we're going to do is we're going to use modal analysis to find out what the natural frequencies are. And so this is exactly the same as Ansys Activity 7. Okay. So no different there. But it's going to be important to know what the natural frequencies are, because it's going to help us interpret the harmonic system response better. Okay. All right, and let's hope and pray that I don't run into any bugs. So I actually ran into a lot of bugs when I was making this handout. Okay. All right, so just like we did before, I'm going to go ahead and suppress these parts just so we have just one bike crank to look at. Okay. For the mesh, I'm going to set the order as quadratic. Okay, just like we always do in a structural simulation. And then for the element size, I'm going to set it to be 2 millimeters. Okay. Let's go ahead and generate the mesh. Okay. And so here is our mesh. And so, again, for modal analysis, you don't need the finest mesh in the world, but it does help to have a decent one, as with any finite element application. Okay. All right. And so we're going to need to fix this thing. Okay. So let's go ahead and add a fix support. And just like we did in Activity 2, we're going to specify it at the 3 holes over here, which is where the bike crank attaches to the bike. Okay. All right. So there's our fixed support. And so our bike crank is fixed on one side. It's free to rotate on the other side. And we're going to do a stress-free or no pre-stress version of this. And so we're going to go ahead and click solve. Okay. All right, and so that should solve successfully. And then from here, you can see all the natural frequencies. Okay? And so you can see our lowest natural frequency here is 196.17 hertz. Our second natural frequency is 450 hertz. And then it jumps up dramatically from there. Okay? All right, so I'm going to do this. And so this is going to be important, for us to view the results. So I'm going to go ahead and view all the different mode shapes. Okay. And I'm going to focus my attention on just the first two modes. Okay. All right, so remember this first mode here corresponds to a natural frequency of 197 or 196, excuse me. Okay. And it's a little bit hard to see just from the still image, but I think it'll be more clear when I play it. Okay. You can see that this natural frequency corresponds to deformations that occur, kind of like perpendicular to the bike crank. Okay. And so, not the same as the deformation that we use for activity 2. Okay, so this is kind of bending along kind of I call this kind of the short axis here because it's kind of thin in this direction. So if you bend it kind of into the page like this, then it's a little bit easier to do. Hence, we have a lower natural frequency here. Okay. All right, and then if we look at the second mode here, okay, so remember this is for 450 hertz. An entire semester and I've gotten worse at writing with a mouse. Okay. Okay. And so you can see the deformation mode for this one is in the Y direction. And so this is consistent with how we loaded it back in activity 2. Okay. And so you can imagine that, the way that we get this deformation mode is that if you have like a vertical force here, and so if you have a force that kind of goes in this direction, that kind of oscillates up and down, right? That's how we get that mode. Okay. All right. And so those are the lowest two deformation modes, okay? And so we can see what their shapes look like. And remember, even though we're viewing results as like a deformation, remember that these deformation values here they're not real deformations, okay? And so remember, the only reason we have these deformation values here is to give you a sense of what the relative shape looks like, okay? And so even though it's saying that it's just displacing by 98 millimeters, which is like kind of crazy, which is like the entire length of this entire thing, right? It's not actually displacing by that much, because these are just the shapes, right? And so in order to get true deformation values, we need to actually run a harmonic response, which is actually going to apply an oscillatory load to this, okay? And so that's what we're going to do. That's what we're going to do in this kind of walkthrough here. Okay. All right. Any questions on this so far? Okay. All right. So this was kind of just a quick review of activity 7. So that's basically all we did in activity 7, minus all the kind of extra stuff I had you guys do. All right. So I'm going to go ahead and close mechanical, and so we're going to come back to workbench here. Okay. And so our next goal here is to do a harmonic response. Okay. And so you can see harmonic responses here, okay? Here's the part where you have to be really careful, okay? And it took me half a day on Friday to kind of realize what this bug was. And so I actually don't know if that bug still exists on here or if it was just my laptop being weird. But when you create this harmonic response, you're of course going to link it with the modal analysis, right? Because those are kind of two, you can almost think of the harmonic response as kind of like the follow-up study after you do the modal analysis, okay? But you have to be careful. And so I think the tempting thing to do is to click and drag the harmonic response onto the solution like this, okay? And so with this, you kind of link the geometry, the mesh, the boundary conditions, and the solution from the modal response into harmonic, okay? You don't want to do this because it might lead you to do some errors, okay? And so just to give you, and so this took me a while to debug, but it looked like what was happening was that when you have a linked analysis like this, and the solution from one analysis is used as an input for the next one, what Ansys is doing is that it saves the results from this one, from the first analysis, as a single file, right? And so I think it's called a .db file, which is basically like database, okay? And so it's saving the results of the modal analysis into a single db file, okay? And then when you run the harmonic response is supposed to read that database file and then use that as input for its own analysis. Okay? What was happening, and I'm not sure if this is a bug or not, was that when I ran the harmonic response, the db file from the modal analysis was getting deleted. Okay. And so the db file was getting deleted, and so when you run the harmonic response, it's saying, "Hey, there's no db file. I can't run the analysis." And I said, "Yeah, no shit, Sherlock. You deleted the db file. No wonder you can't run the analysis." And so, I wasn't able to run the analysis like this, which is actually kind of the recommended way to do it. Okay. but I was able to get it to run like this. Okay, and so instead of linking the harmonic response to the modal solution, what we're going to do instead is we're just going to link the geometry and the mesh. Okay, and so when you click on harmonic response, you're going to drag it on top of model right here. Okay. Okay. So don't drag it on top of solution, because that's going to cause an error. Okay. So the only thing that we want to link between the harmonic response and the modal is just the geometry and just the mesh. Okay. And so that's what we're going to do here. Okay. So I'm going to go ahead and double click on setup. And this is going to open up Ansys Mechanical again. Okay. Actually, let me do this just to kind of remind ourselves, because it's going to be relevant later. Okay. Let me write out the two natural frequencies. Okay. All right. And so those are the two natural frequencies we got from the modal analysis. Okay. And so if we do that, then we have our harmonic response here. Okay. And you can see we're using the same mesh as before. Okay. Right. And so the difference with harmonic response here is that we're going to actually apply a load to this. Okay. All right. So let's go ahead and apply the boundary conditions. Okay. And first thing we're going to do is we need to apply a fixed support. Okay. And so just like we did with modal, we're going to fix the 3 holes here. Okay. And then unlike the modal analysis, we're actually going to supply a force. Okay. All right. And so this force is actually going to provide some kind of external stimulus to our model. Okay. And that's going to generate a vibration response. Okay. Which is going to depend on frequency. Okay. All right. So just like we did in activity 2, I'm going to apply the force here at the very end. And so I'm going to select this kind of inner loop right here. Okay. And then just like we did in activity 2, we're going to set the components for this. Okay. And the first thing I want to do is I want to simulate vibration for the first harmonic mode right here. Okay. And so if you remember from the modal analysis, that vibration or that natural frequency was causing a vibration in the z direction. Okay. And so I'm going to go ahead and add a z component here. Okay. And so I'm going to add a z component force of 100 newtons. Okay. But remember, because this is a harmonic response, this is not a static analysis. Okay. This 100 newtons right here, this is the magnitude of our oscillation. Okay. Okay. And so in reality, what Ansys is going to do is that it's going to apply the force like this. Okay. And so if we draw a XY plot, or I should say YT plot. Okay. So the x-axis or the x-axis is time. And so it's going to apply a force that kind of changes with time like this. Okay. And so the force here is actually going to vibrate, but the magnitude of this is going to be 100 newtons. Okay. And so basically what you're specifying here is the maximum, the maximum amplitude of the vibration. Okay. And we're starting in the z direction because that's the direction where our first modal shape was occurring. Okay. Okay. And so we applied the boundary conditions here. And so are there any questions on this so far? Yeah.
Why did you pick 100?
Yeah, that's a good question. So I picked 100 here, just mostly as just a dummy number. And so most of the time you would actually pick, what the magnitude of your vibration forcing is going to be. And so, I know a lot of you are interested in doing an analysis of an earthquake on the building for the final project. And so, you would actually put kind of the force amplitude of what the earthquake is here for that. But I just put 100 here just to kind of make it simple. Yeah. Mm-hmm. Yeah. For the building, actually, there's a couple ways that you can do an earthquake, and I do want to talk about that briefly after we do this. Yeah. Okay. All right. Any other questions on this? Okay. All right. And so next thing we're going to do is we're going to set some analysis settings. And so if you notice here, the analysis settings has a question mark. Okay. And so that means it wants us to do stuff. Okay. Okay, and so I think this is probably the more difficult part of harmonic response, because we do have to change some settings here, and not all of them are super intuitive. Okay. All right, so the first thing we have to do, and the one that's highlighted in yellow here, is what's called the range maximum. Okay, and you can see from the entry here that it's expecting something in hertz. Right, and so for this analysis, I'm going to specify a maximum hertz or maximum frequency of 500 hertz. Okay. And so what we're saying with this is that Ansys is basically going to check, the vibration response of this force for all frequencies in between 0 and 500. Okay. And so that's why this analysis is called harmonic system response, because we're checking all harmonics for all frequencies up to a certain maximum. Okay. And so, of course, you can set the minimum here as well. But 0 hertz is actually pretty useful, because 0 hertz tells you what the static response is going to be like. Okay. And so I'll just leave the minimum at 0. Okay. But I chose 500 to be the maximum here, is because, if we look at the modal analysis, the highest natural frequency that we're going to be looking at is 450. And so we want to make sure that we capture that in our harmonic response. And so that's why I set the upper bound here to 500. Okay. All right, number two. Number two, we're going to set this, we're going to make this setting here called cluster results. And so by default, that's no. And so we're going to change that to yes. Okay. And if you're wondering what this setting does, is that it makes the plot look a little bit smoother. Okay, so it's kind of a nice post-processing kind of result to look at. Okay, and it'll be easier to explain once we actually run the simulation. Okay. All right, and the last thing we're going to set is you need to expand this setting here for damping controls. Okay, and the setting that we're going to change here is called the damping ratio. Okay. All right, and so actually, if you're running the harmonic system response, you might run into this warning right here, which tells you that the system is being solved without any damping. Okay, and so if you read the tooltip here, is that this may cause very large peak harmonic responses around the natural frequencies due to resonance. Okay, and so what that basically is saying is that without any damping in the system, and damping represents things like friction and internal imperfections in the solid. Okay, and so without damping, what happens when you reach resonance is that the deformations kind of go off to infinity. Okay, because there's really nothing that's inhibiting the deformations anymore. Okay, and sometimes you might want that, but for a lot of times you actually want to keep the deformations bounded. Okay, and so we're going to go ahead and set the ratio here. And so what you actually set for the damping ratio is not super important, because it's not that major an effect. Okay, but something usually in the order of 0.01 or 0.1, anywhere in between those is fine. Okay, the only thing that really matters is that the damping exists and that it can help control some of the resonance. Okay, and I'll talk about it a little bit later after we get the results. What the results would look like if you didn't have any damping in the system. Okay. Okay, so those are the three main settings that we're going to change here. Okay, so any questions on this? Okay, all right, and so the last thing we're going to add here is we're going to add something that for the results. Okay, and so we're going to right click on solution B6. We're going to go to insert. We're going to go to frequency response, and then we're going to go to deformation. Okay. Because usually what we're interested in harmonic response is we want to see how the deformation is being affected by the vibrations at different frequencies. Okay, and so this is exactly what we're going to do here. We're going to go ahead and click that, and so you can see here we have a frequency response object, and so we need to select the geometry for this. Okay, so I'm going to go ahead and select the end of the bike crank. Okay. Right, and so what this is saying is that we're going to check for the displacements of this face right here. Okay, and so that'll be good. Okay, so this makes sense here because this is the part that's at the very end of the bike crank, and this is kind of where we're applying our forcing, and so we can kind of see the direct effect of our forcing on this part of the bike crank. All right, and the last thing we're going to do is we're going to change the spatial resolution. And so instead of using an average result, we're going to change it to maximum. Okay. And so that's going to give us a little bit of a better sense of how much resonance is affecting the deformation. Okay. All right. And so with all those in mind, oh, sorry, one more thing. We need to change the orientation here. Okay. And so, because we're interested in resonance in the Z direction, right? Because that's the direction we're applying our forcing. We're also going to check the deformation in that direction as well. Okay, and so we need to change the orientation here to z-axis. Okay. All right. And so now that we've set the boundary conditions, the oscillatory boundary conditions, we've set the analysis settings. Specifically, we've set the maximum to be 500 hertz, and we've set the damping ratio, and we're all set to check the frequency response spectrum. We are now ready to go. And so with all of those set, we can go ahead and click solve. Right. Takes a little bit of time, but it's not the fastest one in the world, but it's not as slow as optimization or dynamics. Okay. All right, and so the result that you get looks like this. Okay. And so if you remember, when we had our lecture on modal analysis and vibrations, we talked about the concept of a spectrum response. Okay. And so what this is telling us is, for the various frequencies, and so it basically tested a bunch of frequencies in this range right here. Okay, so starting at 0, ending at 500, it measured what the deformation in the bike crank actually looks like. Okay, so let's go ahead and break this down. Okay, and so let's start at the left-hand side, right? And so on the left-hand side, we have a frequency of 0 hertz. Okay, right. And so if something is oscillating at 0 hertz, then it's not oscillating at all. And so this is basically our steady case. Okay. And so when we have a steady case, and so when the force is just being applied with no oscillation, and so this is just a single force in the z direction, you can see that we get a deformation about 0.45 millimeters. Okay. And so that makes sense, right? And so because we're applying the force statically, the structure is going to respond, and it responds with a deformation of 0.45 millimeters. Okay. All right, so that's the first thing. So that's the first thing that we're going to look at. Okay. Next, let's look at the peak, because obviously that's kind of one of the more important ones to look at. Okay. And so the peak deformation here, this tells us that resonance is occurring around this peak. Okay. Okay. Because remember, when resonance occurs, we basically get very high amplitude response oscillations, that result. Okay, and so if you compare the amount of deformation that we get at the peak compared to steady, right, you can see that the peak value here is about 2.35 millimeters. Okay, and so if we compare that 2.35 and we divide it by the steady state one, which is 0.45, okay, we get something that's around maybe 5, maybe a little bit over 5. Okay, and so this tells us that when we have resonance in this structure, we're gonna get a deformation that's about 5 times greater than the steady state one. Okay, which is significant, right? So you're talking 5 times deformation for anything. That's really big. Okay. Next thing I want to point out is, I want you to look at what frequency at which this is occurring. Okay, and so if we kind of trace this down, you can see that it occurs a tad shy of 200. Okay, it's hard to really pinpoint it exactly, but you can kind of see that it's happening right before 200. And so what else do we have here that is a frequency that's right before 200? We have our natural frequency, right? And so if you remember, our natural frequency in the z direction was 197 hertz. Okay, and then from the harmonic response, we see that we get resonance at 197 hertz. Okay, and so this kind of proves the result of the modal analysis to show that we actually do get resonance in this case. Okay, and so what's different? But what's different here, though, is that we're actually getting a real deformation here. Okay, And so unlike the modal analysis where, I told you that you can't trust the deformation values, these ones you can actually trust. Okay, so trust. Okay. Because what's different between this and modal? For this one, we actually applied this force, right? We actually applied a force. We actually applied a load with the real magnitude, okay? And it's a force that oscillates, okay? And so this deformation that we're getting is a direct result of this force, right? Both the frequency, but also the magnitude that we specified here. So the 100 newtons, right? And so the 100 Newton force is forcing the bike crank to displace or deform by 2.35 millimeters, okay? And so when you perform harmonic response analysis and you actually apply real values of the load, this is what you can expect to. Yeah.
For some reason, my deformations are tiny.
How much load did you put in? Would you put 100 newtons for that one?
I did, yeah.
How tiny are they?
3.1284 e to the -2.
Are you looking at millimeters or is this meters right here?
That's millimeters.
Oh, that's strange. I'll take a look after let me finish up this workshop. Yeah. Okay. Any other questions on this part here? Okay. All right. And so that's resonance in the z direction, right? But we also had resonance in the y direction, right? So let's go ahead and change our components here. Okay. And so to simulate resonance in the y direction, I'm going to go ahead and change this. And so instead of forcing in the z direction, I'm going to apply the forcing in the y direction. Okay. So I'm going to apply 100 newtons in the y direction. And then for the frequency response here, instead of looking at the x-axis orientation, we're going to look at the y-axis orientation. Okay. Right. And so now what we're actually going to plot here is deformation in the y-axis. Okay. So let's go ahead and hit solve, and we'll see how our deformation response changes.
I think I found that error.
Ah, okay. Good. Okay, and so here is our response, okay? And you can see here now the peak has shifted, right? And so now, because now we're looking at the deformation in the y direction, okay? You can see here that we reach a peak at this point right here. And if I could draw straight lines, what you'll see is that this is kind of right in the middle between 400 and 500. It's getting worse the more I draw. Okay, and so it's occurring kind of right around here, right? And so, oh, I erased it. But if you remember from the modal analysis, our second natural frequency was 450 hertz, okay? And so you can see here from the harmonic system response that we're getting resonance at that exact same place, 450 hertz, okay? And so again, this confirms, what we got in the modal analysis. The difference here is that, these deformations here, you can actually trust it, okay? And so by applying this, this oscillatory force, we're getting resonance around this much. And so for this particular case, we have huge load, we have huge deformation amplification, okay? And so our steady state, our steady response for a 100 Newton force in the in the y direction only gives us an amplitude, deformation amplitude of about 0.1 millimeters. But for resonance, we can see that this jumps up to 0.458. Okay, so that's a huge increase in the deformation. Right? And so, this just kind of shows you how dangerous resonance can be, for certain structures. Okay. All right, any questions on this? Okay, so let's talk. Let me talk briefly about what you can do to simulate an earthquake. Okay, and so to simulate an earthquake, specifically for the two-story building that I give you, for the project, you can do it this way too. Okay, and so you can apply a force to the building, except that you would of course have it vibrate in one of the horizontal directions. Okay, and so that's possible. The difficulty with that is that you still have to fix the building somewhere. Okay, And so what you're going to most likely want to do is you're most likely going to want to apply the oscillatory force on either the columns or the bottom of the columns. Okay. And so, if I draw, let me just draw one story. Okay. Right. And so ideally, you would want to apply the oscillatory force here. Okay. Because that's where the earthquake's going to be hitting the ground. Okay. The difference for this is the difficulty with this is that you also need to use the bottoms of these posts as fixed supports, right? Because that's where it's fixed to the ground. And so if you apply a force there, that force actually won't transmit to the rest of your structure because that's also a fixed support. Okay. And so a couple ways you can do this. And so one way that you can do it is you can keep the bottoms fixed, but you can apply the oscillatory force kind of on the first floor or kind of at the tops of the columns if you want. Okay. And so that's one way that you can do it. Another kind of clever way that you can do it is that instead of applying an oscillatory force, what you can do is you can apply an oscillatory displacement. Okay. Okay. And so here's kind of our one-story building here. Okay. And so remember, if you remember from activity 5, one other type of boundary condition that you can do is a displacement, right? So let me go ahead and suppress this for now. Okay. And so displacement basically will help you define, how the displacement of a certain part changes as a function of time. Okay, so let me go ahead and do this right here too. Okay. And so let's say I wanted to apply an oscillatory displacement in the y direction. Okay. And so let's say that we have a displacement of 2 millimeters in that direction. Okay. And so what this is going to do is that it's going to apply a displacement that goes up and down here, okay? And then it's going to see what the response looks like from there. Okay? And so you can apply that here as well. And so if you apply a displacement, an oscillatory displacement on the bottoms of these columns, which is kind of what you expect from these, okay? Then that's going to cause the whole building to kind of sway, with that displacement, okay, which is what you want to look at. Okay? The only thing I would warn you about is that if you are going to use this this method right here where you apply a displacement, you should measure your deformation at a different location. Okay, and so if I actually ran the simulation right now, it actually wouldn't make any sense because we're applying an oscillatory displacement here, but we're also measuring what the displacement is here as well, and so we're kind of like prescribing what our solution looks like. Which is not what we want, right? So what we want instead is we want to see how the system kind of naturally responds to external effects, okay? And so if you are going to do an oscillatory displacement on the building, you can apply the oscillatory displacement on the bottoms, but then when you measure, go ahead and measure the frequency response, do it on like one of maybe the first floor platforms or the second floor platforms, okay? That way they're far away from the displacement boundary conditions, okay? And so what's going to happen is that you're going to apply a displacement boundary condition on the bottoms of these columns, and that's going to cause the tops of the buildings to sway. Okay, and so you want to see how much the tops of the buildings are swaying, and so you should do your frequency response on the upper column or on the upper platform like that. Okay. All right. So that's basically how I would approach doing an earthquake response on that building or just any building in general. Okay. Okay. Any questions on this? Yeah.
We don't have to apply fixed supports if we use displacement, right?
So the displacement also counts as a constraint, and so it's not the same as fixed support. So fixed support says the displacement 0, but when you apply displacement, you're specifying what the values of the displacement are. And so the main goal of the fixed support is to prevent any kind of rigid body motion. And so you should be okay. You should be okay just to use a displacement support here because it does count as a constraint. And so remember the only requirement for finite elements is that you have at least one constraint. Yeah. And so you should be okay. But if you are running into issues, you can maybe just fix one of the columns here and then apply the displacement force on all the other columns. Yeah. Mm-hmm. Okay. All right, and so that's harmonic response, and so hopefully that's useful for you guys. Okay. right, so the next thing I want to go over today is thermal simulations. Okay, so I don't think we'll be able to get to the example, but I did want to talk about some of the theory behind it, because we haven't talked about heat transfer at all, and heat transfer is a whole nother class. And so I do have to cover some of the theory, just because it's important. We need to do that just to understand what the settings are in Ansys. But from there, and then from there, we'll be able to do an example. Okay, so let me go ahead and stop sharing here. Bring back the good old iPad. Okay. And we're going to talk about thermal simulations in Ansys. Okay. And so this is a kind of almost like a completely new realm of theory. Okay. And so it's still finite elements, but thermal sciences is just by nature very different from structures. Okay. So has everyone taken a heat transfer class before in their undergraduate or semi recently within the last 5 years or so? If not, it's okay. We're gonna cover all the main concepts from scratch, but leveraging that information from the past will definitely be helpful. Okay. As we are going to go kind of fast, because I do want to get to the example. Okay, and so the whole idea with heat transfer simulations in Ansys leverages the fact that finite elements is way more than just a framework for doing structural simulations, right? And so if you remember from the very beginning of the class, we talked about how finite elements is really just a method to solve any differential equation. We've mostly just been focusing on one differential equation, which is the structural one, but there's so many others out there. And the thing about most physical phenomenon, at least in the way that the theory around them has developed, by Newton and all those guys, is that they've used differential equations to describe physical behavior. Okay, and so one such equation is the heat equation. And actually, mathematically, the heat equation is, and I want to be careful here because I don't want to piss off any other faculty, but the heat equation is mathematically simpler and easier to solve than the structural mechanics. Okay, and so the heat equation, kind of in its kind of most basic form, looks like this. And I'm going to write the 2D one. Okay. And so this is kind of the heat equation in kind of its purest form. Okay. And trust, and I know it looks kind of scary, but trust me when I say this is actually easier to solve than the structural mechanics one. Okay, if you are interested in actually solving this, I am teaching. I don't know if I'm teaching it, but I'm most likely to be teaching a class next semester, EGME 417, called Computational Heat Transfer, where we actually do solve this. And so, I need to plug one of my classes from here. Okay, and so let's go over some of the key terms here. And so we have T, obviously. Okay. Big T. So big T here is the temperature. Okay. U and V here are the convection velocities. Okay. Okay. And so, convection is the idea that when you have some kind of moving fluid, and so let's say that you have airflow or you have water flow, then that enhances heat transfer. Okay, and so that works its way into the equations, with those convection velocities and those first order derivatives. Okay. K here is the thermal conductivity. Okay. And so the thermal conductivity is probably our most relevant material property here. Okay. And so the thermal conductivity expresses how easily heat can actually move through this material. Okay. And so if you have a metal, and so metals are great conductors of heat. Okay. If you've ever touched a hot frying pan, you will agree with me. Okay. And so the thermal conductivity for metals is extremely high. But for certain materials like styrofoam, the thermal conductivity is very low. And so that's why you can pour hot coffee into a styrofoam cup and it won't burn your hand. Okay. Okay. And the last term here is Q dot. And so Q dot here stands for thermal generation. Okay. So thermal generation is the basically any way for the material to kind of internally generate heat, either through some kind of chemical reaction or maybe through some electricity. Okay. Okay. And so the equation is different than structures, and of course all of the material properties, all of the solution variables, all the boundary conditions. They're of course going to take different forms because naturally we're solving something with completely different physics. Okay. But with that said, just because it's a whole nother equation doesn't mean that we can't solve this in finite elements. And so what I'm going to hope to prove to you today is that we can take all of the knowledge that we've gained in this class on structural finite elements and just apply it in a different way to thermal. Okay. And the idea is to take, a thermal concept and kind of map it onto a structural concept. Concepts of like constraints, things like loads, meshing is going to be exactly the same. Things like, the solution field is what they look like. Okay. And so even though it's a whole nother equation, we've learned, I would say about 75% of what you need to, you've already learned 75% of what you need to know, maybe even more than that, maybe 85% of what you need to know to actually run a thermal simulation. It's more just kind of, matching up the terminology where it's relevant and kind of connecting those ideas with your background knowledge on heat transfer. Okay. Okay. Any questions on this? Okay. All right. So let's talk about all the things that are staying the same. Okay. And so for all of our structural simulations, our starting points are always going to be to load in the geometry or create the geometry, define the connections if we have any, if we have separate parts in our assemblies, and to perform the meshing. Okay. The great part about thermal simulations is that thermal simulations require all this too. And so all of this is exactly the same as how you did the structural simulations. Okay. It's literally exactly the same. You don't do anything different here. Okay. Oh, we are doing thermal. Should be exactly the same as structural simulations. Okay. Okay. Well, actually, there is one small difference that you can make, and this is an optional change, and so you don't have to do this. But because we're running thermal simulations, and because the governing equation here is a lot easier to work with than the structural ones, we have a little bit more flexibility in terms of the mesh. Okay. In particular, we have flexibility in terms of the element order. Okay. And so the nice thing about thermal simulations is that you can actually use linear elements. Okay? And so up to this point in the class, you might be thinking that linear elements are absolutely useless because we literally never used, well, we did use them in dynamics. But, for most cases, we haven't used linear elements at all. But for thermal simulations, because the governing equation is relatively easier to solve, we can use linear elements here and it's not going to cause an issue. And actually, I think for most cases, it's actually preferred to use linear elements versus quadratic numbers. Okay. But again, it's at the end of the day, it doesn't make that big a difference, but but linear elements are okay here. So you don't have to worry about shear locking or anything like that. Okay. Okay. And so, but largely, outside of that, you can apply exactly the same process that you've done for structural simulations. Okay, so now let's talk about the boundary conditions, and here's where things start to get a little bit, a little bit different. And so since we're running a thermal simulation, the nature of the boundary conditions that we're going to apply have to also be thermal boundary conditions, okay? And so we're not going to be applying any fixed supports, we're not going to be applying any pressure loading or force loading or bearing loads or anything like that, okay? And so we're actually going to we're actually be applying, thermal conditions on the outside of our structure, okay? The good news about this is that, even though the terminology is really different because they're thermal boundary conditions, they still take mathematically the same form as the structural ones, okay? And so what I'm going to do is I'm going to go over all of the main thermal boundary conditions that you can apply, and I'm going to categorize them as either a constraint or a load, just so that you can kind of connect it together with the structural simulations, okay? Because mathematically, all of these kind of work in exactly the same way, okay? All right, so number one. And so the first, and probably the one of the more common boundary conditions that you can apply in thermal simulations is a temperature boundary condition. Right. And so the temperature boundary condition, just like its name implies, is we're going to directly specify what the temperature is going to be at a particular surface. Okay. And so, let's say that we have a cylinder like this, okay? And then let's say that, we know that the temperature of the cylinder on the left face, okay? We know that the temperature here is going to be 100 degrees C. Okay. Right, and so we can directly specify that. And so we can directly specify what the temperature is going to be at a surface using a temperature boundary condition. Okay. Okay, and so how does this compare, or what's the analogy between this and our structural simulations? Okay. The temperature boundary condition is, I think, our only one, and so this is exactly the same as applying some kind of constraint. Okay. Okay. And so this is kind of the same thing as our fixed support, as our displacement constraint, okay? And so that mathematically this performs the same purpose, okay? Because remember, remember when we talked about boundary conditions earlier on in the semester, right? And so the thing about constraint type boundary conditions is that they directly specify what the primary solution variable, what value it's going to take. And so in structural finite elements, remember our primary solution variable was our deformation, right? And so when we apply a fixed support where we say the deformation is 0, then that counts as a constraint. Okay? For a thermal simulation, our primary solution variable here is the temperature, right? Because that's the main variable that occurs in our differential equation. Okay? And so the first thing that Ansys solves for in a thermal simulation is the temperature at all locations in our mesh. Okay? And so a boundary condition that directly specifies this, this variable at a particular surface, it has to be categorized as a constraint. Okay? And so when you directly specify the temperature, that's the same thing as applying some kind of fixed support. Okay? And remember, the thing about constraint type boundary conditions is that you have to have at least one in your simulation. Otherwise, the simulation just won't run. Okay? And so no matter what kind of thermal simulation you're going to run, you have to have at least one temperature boundary condition somewhere to kind of set the baseline for what the other temperatures are going to be. Okay. All right. Any questions on temperature boundary conditions? Okay. All right. So that's temperature boundary conditions. So next we have heat flow and heat flux, and so I kind of count these as the same, even though Ansys kind of separates them. Okay. And so heat flux and heat flow boundary conditions, these are our primary load type boundary conditions, okay? Right. And so this is actually almost directly analogous to a force boundary condition. Okay, so heat flow is like a force. Okay. And heat flux here is basically the same as a pressure, okay? Because heat flux is nothing more than heat flow divided by area, okay? All right, so what do these do? And so heat flow and heat flux boundary conditions, they require the specification of the total amount of heat going through a surface. Okay. Okay. The key word here being heat. Okay. And so, the whole central idea of heat transfer is that, whenever you have a region of space or any kind of object that's hot on one side, okay, and the other side is cold, okay. Whenever you have a temperature difference like this, energy is gonna move from the hot region to the cold one, okay. And that's basically how all of heat transfer works. And so heat always goes from something that's hot to something that's cold. Okay. Whenever I teach heat transfer, I always joke in the first day of class and say, all of heat transfer can be summed up as heat goes from hot stuff to cold stuff, and then that's all you need to know about heat transfer. And so we're just going to screw around for the next 15 minutes. But of course, there's a lot more nuance than that. But that's essentially how heat transfer goes. And so the quantification of the energy that actually moves here, okay. Okay. And so the amount of energy that actually gets transferred through a heat transfer process like this is what's known as heat. Okay. And so that when we talk about heat, what we're actually talking about is the movement of energy due to a temperature difference. Okay. Okay. And so this type of boundary condition can be really useful because a lot of engineering processes are rated or they're defined by how much energy that they give off. Okay. So let me give you a couple examples about how these can be useful. Okay. Because I think this is the boundary condition that people tend to that kind of intimidate people when they're using thermal simulations. But let me give you a couple examples of where this would be good. Okay. All right, so one example could be like a combustion chamber. And so let's say that you want to compute or solve for how the temperature in your car engine is changing as a result of a combustion reaction inside the engine. Okay, and you want to specify a boundary condition on that combustion chamber. Okay. And so unless you have thermometers inside the combustion chamber or specifically on the walls of the combustion chamber, it's really hard to determine, what temperature that is exactly what temperature is inside that combustion chamber. Okay, that's really hard to do. But what's easier to do is that chemically, like how much oxygen and how much air and how much of fuel is being added into the combustion chamber, and so you can quantify, with relative accuracy, how much energy that combustion reaction is giving off, right? And so if you were running this thermal simulation on your engine, and you're applying a boundary condition on the combustion chamber, you can apply a heat flux boundary condition or a heat flow boundary condition that is related to how much energy that combustion reaction is giving off, okay? Because what you can assume there is that, all the energy from the combustion, from that little explosion, all that energy is going to pass through your engine in the form of heat. Okay, and so what's I think the most appropriate boundary condition that you could do there is a heat flux, heat flow type of boundary condition. Okay. Another useful example is electric heaters. Okay. And so electric heaters, they're often rated by how much energy that they can output, right? And so that energy comes directly in the form of heat. And so if you're running a simulation of, you want to determine what the temperature in the room is going to be, right? But you have a little electric heater on the wall. You can apply a heat flux boundary condition coming from that heater, based on how much energy that based on the wattage or based on the power of that electric heater. Okay. Okay. Any questions on this? All right, and so the reason I call these low type boundary conditions is because if you apply a heat flux onto your geometry, then that's going to cause the temperature to either rise or fall. And so you can think of it as your structure or your geometry thermally is reacting to what the heat fluxes and the heat flows are going to do by changing its temperature. Okay. All right, so the next one we're going to cover is the perfectly insulated boundary condition. Okay, and so the perfectly insulated one is actually not a unique one by itself, and so this is actually a very special case of the heat flux heat flow type boundary condition. Okay. And it's a special case because a perfectly insulated boundary condition is one where the heat flow is zero. Okay. And so if you kind of remember from your heat transfer classes, when we say that something is perfectly insulated, what we say is that no heat can pass through the surface. Okay. Okay. Right. And so this is a useful boundary condition where if you don't expect any heat to pass through a particular surface, then this is how you can do it. Okay. I will say that the perfectly insulated boundary condition is an approximation. Okay, in reality, it's impossible to have something that's perfectly insulated, and so no matter how good your material is, some heat is going to pass through it. Okay, it might be a very small amount of heat, but just by the laws of physics, whenever you have any kind of temperature difference, heat is going to pass through that surface whether you want it to or not. Okay, you can design your material to limit the amount of heat, but it's still going to happen. Okay. So even if you have a hydro flask, if you leave it out for a few days, the water inside is not going to be cold anymore. It's going to heat up eventually. Okay. And so those are the main constraint and load type boundary conditions. Let's talk about some more kind of specialized thermal boundary conditions that don't have maybe an exact analog to structures, but they're very important for heat transfer. Okay, so now let's talk about a convection type boundary condition. Okay. And so just like I mentioned before, convection is the heat transfer usually from one solid object to a moving fluid. Okay. Okay. And so just like we mentioned before, whenever you have some kind of moving fluid, the moving fluid is always going to enhance the heat transfer. Okay. Think about, when you're standing outside and it's windy outside, right? And so whenever there's wind blowing, it always feels colder than what it actually is because of the wind chill factor, okay? And so the wind chill factor is nothing more than just convection, okay? And so even though the temperature outside may not be that cold, if the wind is blowing, then your body is just, losing a lot more heat than if the wind were still, okay? And so, because of that enhancement by convection, then it feels like it's colder than it actually is. Okay. If you're into cooking, the air fryer works. The reason it works is because of convection. Okay. And again, it uses the moving air to kind of enhance the amount of heat that's going into your food. Okay, among other things, but that's one of the main reasons that it does that. Okay. Okay. And so this is a very common, of course, occurs very commonly for engineering practice. And so we need a boundary condition to handle this. Okay. All right. So schematically, it looks, whenever we have convection, we always draw a figure that looks something like this. Okay. And so here, let's say we have a surface. And so the temperature of the surface, we'll call it TS. Okay. And we have some kind of moving fluid on top. Okay, so we have fluid that's moving past, and the fluid has a temperature T infinity. Okay. Okay. Where TS right here is surface temperature. Okay. The heat transfer that you experience as a result of convection is given by the following equation. Okay. And so the heat transfer is equal to H times A times the difference between TS and T infinity. Okay. And the name of this equation right here, this is called Newton's law of cooling. That's more trivia than anything, but I always just call this convection formula. But sometimes I'm scared that Newton will come up from his grave and stab me if I don't give him credit for his equations. Okay. And so the reason I bring this formula up is not to discuss its origins, but to talk about it from a perspective of, what do you actually need to specify in Ansys in order to make this happen? Okay, because convection is almost always going to be there, and so unless you're working on a very specific application, you're almost always going to have some kind of air cooling, or you might have some water cooling, right? And so convection is always going to be there. And so, knowing how to correctly specify this in Ansys is an important skill for anyone that's doing thermal simulations. Okay. All right. Any questions on this? Okay. So let's go ahead and define the terms of this equation. Or actually, we have a lot of these already, but let's define them in terms of what you actually need to specify in Ansys. Okay. And so when you specify convection on a surface, of course, you need to specify what surface you're going to apply the boundary condition on. Okay. In addition to that, you need to specify these two terms from that equation. Okay. First of all, you need to specify T infinity. And so you need to specify the temperature of the fluid. Okay. Because a lot of times, when you're running a thermal simulation, you're not expressly meshing, or you're not expressly solving for the temperature in the fluid that's around your structure. Okay, or it might be fluid inside your structure, right? And so you need to specify what that temperature is in order to specify a convection type boundary condition. Okay, and a lot of times this is usually not that hard to determine, right? And so if you have let's say an aerospace application, you're designing, you're doing thermal design of a commercial aircraft, right? And so there's tons of data for, how cold or how hot the temperature is up 10,000 feet in the sky. Okay. And so that's usually not that hard. You just have to kind of, look up the weather data or something like that and plug the temperature. Okay. Okay. The other variable, which I kind of neglected mentioning on the last page, is H. Okay, and H here is the convection coefficient. Okay. And so what the convection coefficient tells you is it tells you how effective that fluid is at transferring heat. Okay. Okay. Because different fluids are going to be able to transfer heat, with different kinds of efficiency. Okay. And this actually depends on a lot of factors. And so the value for H depends on. Okay. Of course, it depends on what fluid that you're running. Okay. Okay. Because each fluid has a different thermal conductivity, and so depending on if the fluid is a good conductor of heat or a bad conductor of heat, it's going to affect its convection coefficient. Okay. It also depends on the fluid velocity. Okay. And so faster fluids, of course, are going to enhance heat transfer a lot more than slower moving fluids, right? If you stand outside in a snowstorm where the winds are going like 40 miles an hour, it's going to feel a lot colder than if it's just a gentle breeze, right? It also depends on the nature of the flow, so whether your flow is laminar or turbulent. Okay. And it also kind of depends a little bit lightly on the geometry. Okay. It's a lot of stuff, and so it depends on a lot of different factors. And in reality, you know, this is kind of way too hard for, you know, people to compute by hand. Okay? But Ansys does actually require you to specify them. And so, you know, I'd say this is probably the most difficult part of running thermal simulations, is determining what the convection coefficient should be. Okay. And so you could, if you're knowledgeable about the flow, you can probably have a good guess for it. But if not, you probably need to run some kind of fluid simulation to determine what this H value is. Okay. And that's probably going to be the subject of the latter part of our Wednesday lecture. Okay. But we are out of time today, and so I don't want to hold you guys anymore. And so, are there any questions on this before we wrap it up for today? Okay. All right. And so on Wednesday we'll finish up the theory on thermal simulations. We'll do a very quick example, and then we'll cover how to do fluid simulations in Ansys as well, because that was number 2 in the poll. Okay. All right, so thank you guys for coming today. I know it's the very last week, so I know everyone must be really tired. So, you know, I appreciate you guys coming out. So hope you guys enjoy the rest of your evening, and I'll see you for our very last lecture on Wednesday.